Hi everybody, in this video I'm going to talk about projectile motion at an angle. So we've already talked about what happens if you launch something straight up, and we've talked about what if you launch it straight across. Well, of course, there's a gazillion other options. How about launching it at an angle? So that's what this is going to talk about today. So if we have a cannon on a level ground shot at a 30-degree angle at velocity of 15 meters per second, what are the initial x and y velocities? In other words, we have to break this up into the components. And so here I drew a little diagram. It's tiny, but my initial velocity is 15 meters per second. But I have to break it down to my y components and my x components. So I need to use some trigonometry, and then that's a 30-degree angle in there. I need to use some trigonometry to figure out what that's going to be like. So let's take the sine of 30 degrees and set that up. And when we do that, that's going to solve for the y direction. And if we take cosine of 30 degrees and set that up, that's going to solve for the x direction. Okay, so if we set up the sine of 30 degrees is equal to opposite over hypotenuse, that's v sub o y over 15, that's our hypotenuse. If we solve this equation, we're going to take this and multiply times 15 on both sides to solve for v sub o y, and we have to make sure we're in degree mode. So when we do that, we get 7.5 meters per second in the y direction. So that launch velocity in the y direction is 7.5 meters per second. We also have to look at the x direction. For the x direction, we want to look at cosine because that's the adjacent. And so once again, I'm going to set it up where cosine of 30 is v sub ox. That's the adjacent over the hypotenuse. So to solve it, I multiply times 15. I make sure I'm in degree mode, and I get 13 meters per second. So whatever is getting launched has an initial velocity of 7 meters per second to the up and in the y direction, and 13 meters per second in the x direction. We need to break those up so we can move on. How long does it take to reach the ground? Okay, once again, I'm going to draw a little diagram, and again, it's very small. But one thing that we know is that the velocity in the y direction when it's at the top is equal to 0 meters per second. And that's a really helpful piece of information to have. We also know that the velocity in the y direction at the launch at the beginning, we found that. It is 7.5 meters per second. So I can lay out my variables, and I can say the initial y velocity is 7.5. The final is going to be 0. I know I have acceleration of negative 9.8 meters per second squared, and I need to be finding my time. So I think I can use this kinematic equation to find out what that's going to be, because I know my final is 0, I know my initial is 7.5 meters per second, and of course t is what I'm looking for. So again, I'm going to keep on solving this. I'm running out of space, so I'm just going to keep going down here. So I'm going to move my negative 7.5, I'm going to subtract that, move it over to the other side, divide by negative 9.8 meters per second squared, and I'm going to get my final answer here. And so when I get that, I get 0.77 seconds. Now remember, that's only halfway across, right? That's going up. It also has to go down. So let's go ahead and multiply that times 2 to get the entire trip. And when I did this, I didn't erase my value, so I ended up getting 1.53 seconds. If you round it and just use 0.77, you're going to get 1.54, and actually 1.5 is enough significant digits for this problem. Okay, all of that green stuff all went with part B. So that, like I said, it got kind of too much space, but let's take a look now at part C. How far away from its initial position does it land? Okay, remember that when we are going in the x direction, this is called the range, and this is the x direction. And so when we are going in the x direction, the velocity is constant. And we already calculated what that was. It is 13.0 meters per second, or just 13 meters per second. And so, because it is constant and it does not change, we can just use our basic definition of velocity formula. And so we're just going to take delta x over delta t gives me the velocity. So I multiply both sides by delta t. Then my velocity, which was 13 meters per second, times my time, which I just figured out is 1.5 seconds, I should put meters per second over here. And I put that into my calculator to get my x, my total distance, my range. So go ahead and multiply that out. And I'm getting 20 meters when I multiply that out. Last part, and then this next one is going to be the next question, so don't worry about that for right now. Next part is the final velocity. Okay, let's go back to one of these diagrams, maybe this very first one, and remember that when it gets launched and when it comes down, they are symmetric. And so whatever's happening at the beginning is happening at the end, just in the opposite direction as far as the y direction goes. So its final velocity is 15 meters per second at 30 degrees below the horizontal, because it went up at 30 degrees, so it's going to come down at 30 degrees. It had initial velocity of 15, it's going to have initial velocity also here at 15. And some people want to put a negative there. If you want to put a negative there, you can. I think having this description is the same thing. But make sure you have the degree, though. You have to have that degree. Okay, this next one I actually have on another slide where I've got more space. Okay, I'm going to do that same diagram. My initial velocity is 21 meters per second. I need to break it up into the x components and the y components. This time it's a little bit easier because it's 45 degrees. Okay, I'm getting 14.9 degrees. I'm going to take the sine of 45 as opposite over hypotenuse, multiply by 21, and I get 14.9 or even 15 meters per second. Now, that is a 45 degree angle. Since it's a 45 degree angle, then they are the same. Both of them are the same. So VOX and VOY are both 14.9 meters per second. Okay, this question, remember, is when I utilize that fact that on its trajectory, when it gets to the top, it has a y velocity of 0. And so the final y velocity, I'm talking just like half the way, final velocity half the way up there is 0 meters per second. Its initial, once again, was 14.9 meters per second. I know my acceleration due to gravity, and I'm looking for time. So again, I can just use this equation. My final, I'm using the 0. My initial, I'm using the 14.9. And then acceleration, of course, negative 9.8. And so I just need to take a minute to plug in my values and work out this equation. Okay, so I divide by negative 9.8, and I get 1.5 seconds, and that is halfway. And so my total time is 3 seconds. Okay, how far away from the cliff does it land? Again, that question is asking in the x direction question. When I'm going the x direction, my velocity is constant in the x direction, and so I can just use my average velocity equation. And so my velocity is 14.9, my is delta x over 3, so I'm going to multiply both sides times 3, and I'm getting 44.55 meters. You could probably round that to 45 meters. And your final velocity, well, it's the same exact thing as it was before. So it is still 14.9 meters per second, but this time it's going down at a 45 degree angle. It's just symmetrical from where it was here. It's a reflection of it. Okay, so I hope you can see these are not much harder than a lot of the other ones we've been doing. It's just we're pulling it all together. We're pulling in the y direction and the x direction together.